So in this class, we will discuss about the diffusion current. We have already studied in previous classes about the drift current. What was the drift current? When we have applied a potential difference across a conductor, then electrons gain energy and they travel from one direction to other direction. So because of this motion, they get some velocity that was called the drift velocity. And because of this drift velocity, because the electrons are moving, so because of the motion of electrons, we call the drift velocity and also a drift current, because the flow of electrons is nothing but it is a current. So we have discussed already the derivation of drift velocity and drift current. Today here we will discuss about the diffusion current. So as the name implies, there is something to diffuse from one side to other side, and because of that there will be some development of the current that will be called the diffusion current. Now if we take a space of a different concentration gradient, whether they are the holes or they are the electrons or maybe the combination of both. So if this concentration gradient exists high and low within a surface, so where the concentration gradient is high, electrons or hole will try to diffuse from higher concentration gradient to lower concentration gradient. This movement may be due to the holes or maybe due to the electrons, and because of this moment there will be a development of the current that will be called the diffusion current. And if this current is because of the holes, then it will be called the diffusion current by holes, and if it is because of the electrons, then we call the diffusion current by the electrons. So we have to derive the relation here. What is the drift current, and then finally we will find out that in a semiconductor material what will be the total current, because total current means sum of the drift current and diffusion current, that will make the total current or total current density. So let us discuss here that the carrier currents are also due to the concentration gradient in the developed material, which leads to diffusion of carriers from high concentration region to lower concentration region. A concentration gradient exists if either the number of holes or electrons is greater in one region as compared to the rest of region. This already I have discussed. When a concentration gradient of carriers exists in a material, the charge carriers tends to move from the region of higher concentration to the region of lower concentration. The process is called the diffusion, and the current due to this process is called the diffusion current. Same thing I have discussed before that. So let us derive the relation. How will derive the relation of the diffusion current? Now first let us assume that we have a reference plane X. This is a reference plane X. We have to assume. And the density of holes is P per meter cube. In this plane X, density of hole is P per meter cube. And let the carriers have a mean free path delta x and mean free time delta t between collisions. Between collision means once one electron have a collision between other electron, So they will travel a small path, that is called the mean free path delta x, and the time taken between the collision, that is called the delta t. So assuming a uniform density gradient of holes, if P is the density of holes in the reference plane x, and since in reference plane x they will move delta x directions either in left or right. So what will be the density gradient? Density gradient of holes will be defined as minus dp by dx, where p is the density of holes and x is the reference plane over which we have to find out the diffusion of holes or electrons. So we want to find out the uniform density gradient of holes in respect of x. That's why we have written minus dp by dx. Why minus we have written here? Because the flow will be opposite to the density gradient, that is from higher density gradient to the lower density gradient. That's why we have used a minus sign. So we have written here minus dp by dx. This is the density gradient of holes. Now let us go to the next slide. We have to find out the average density of holes in this region. So as we know that simple average, how to calculate a simple average between 2 points, that just we take half of that value between the 2 points. So here we assume that at the reference plane one point is x and one point is x minus delta x. Let us go to the previous slide and see. We are taking a reference plane here x, and in first case we are taking a point x, and if we move toward the left, that is delta x distance or delta x path. So we are moving against the higher concentration side. It means density of holes will decrease slowly this side and will increase slowly this side. So that's why we have written x minus delta x this side, and where the density will increase we have written x plus delta x this side, and in center we have x. So if you want to take the average of this density between x and x minus delta x, then simply we'll add both density gradient, that is at x and at x minus delta x, and we'll take half of that. Same procedure is applied here. So what we have written is, that is half of density gradient, that is whole density gradient at x is p, plus density gradient at x minus delta x. So at x minus delta x, what will be? P minus dp by dx delta x. So this will be the average density of holes in region x minus delta x and x. So if we open the bracket and resolve this equation, so this will become p minus half dp by dx and delta x. Now this is the average density of holes which we have found out. Now flow of holes to the right per unit volume. Now let us find out the flow of holes to the right per unit volume. So flow of holes mean, that is the velocity or the hole current. So what is the hole current? In terms of the velocity, that is the mean velocity. So what is the mean velocity? Mean velocity nothing but delta x by delta t. This is the mean velocity. And what is next? Then if we multiply this mean velocity with this value, this density, that is the density is half of p minus half dp by dx del x and multiply by del x by del t. So this will become the flow of force to the right. This will become flow of force to the right. Or you can understand that average mean velocity into average density of force. So what will be the average mean velocity? Average mean velocity will be half of delta x by delta t multiplied by the average density of force in the region x minus delta x. Same thing is written here, and that we have denoted by P1. Now this is the flow of force to the right we have calculated. Similarly, the flow of force to the left we have to calculate in the same difference plane x for unit time. So what we will do, instead of writing here minus, we will use a plus sign here, and rest of the all quantity will remain same. So what we will written here, we can write, that is the flow of force to the left will be P2, that P2 will be equals to the half of P plus half of dp by dx del x and del x by del t. So we have found out two equations now, that is the flow of force to the right and flow of force to the left. Now we have to find out the net rate of flow of force to the right. And since we know that in the reference plane x, the holes are moving from left to right. Why? Just see in the diagram, holes are moving from this side to this side, that is from left to right, because this side is a higher density gradient and this side this is a lower density gradient. So net flow will be, that is P will be equals to P1 minus P2. So already we have calculated both the values here. P1 is this one and P2 is this one. So if you write here P1 minus P2 and resolve this equation, so some terms will be cancelled out. So finally we will get minus half delta x into delta x by delta t into dp by dx. Or we can write this expression in more simplified way, that is dp by dx we have written as it is, and these terms we have taken, this term leaving the minus, this term we have taken as a dh. So we can write minus dh dp by dx, where we have defined here dh is nothing but is half del x into del x by del t, that is half del x square upon del t meter square per second, and this dh is nothing but it is called the diffusion constant. Since we are going to find out the diffusion current, so this is called the diffusion constant. Now let us see here in next case that current density due to the diffusion of force is given by. What is the current density? Current density due to the diffusion of force, that is we have find out minus dh by dh into dp by dx. So this is the net rate of flow of force. So now what we are going to find out, that is the current density jh. It means if you multiply by charge E may be positive or negative, but here since we are taking holes, so this E will be positive. So if you multiply this E with the value obtained here dH and dP by dx, so we can write here the current density due to the diffusion of holes, that is denoted by JH, that is equals to minus E dH dP by dx. This is the current density due to the diffusion of holes. Similarly, the current density due to the diffusion of electrons can be written as, for the case of electrons, we will take E with minus charge. Here we have taken E with plus charge. So here also we take E with minus charge, then this minus will become plus here. So this will become E, and in place of dH we will write dE, because this dH is for holes and here this dE for electrons. And here we have written dP by dx, P is for holes, so here we will write N for electrons. So current density due to the diffusion of currents will be written as J equals to E dE dN by dx. Now we have find out the two current densities because of the diffusion, that is because of the diffusion of holes and because of the diffusion of electrons. So if we want to find out the total current density in a semiconductor, so as we know that in a semiconductor the total current will be because of the drift current and because of the diffusion current. So we have to add both terms, that is drift part and diffusion part, then only we can write the total current density. So first we write the total current density for holes, that is we have denoted by JH. So GH is one part minus E ds dP by dx. We will write simply this part here. And second part, already in previous classes we have studied that the drift current. So drift, for here we will take a drift current as E P mu H, that is in terms of the mobility and density of force and applied electric field. So what is the total current density of force Js, that is E P mu H minus this term. Similarly, we can write the total current density for electrons, that we have denoted by Je. So in place of H we will write E, and in place of P we will write N, and here for electrons we will write this term. So Je will be equals to capital E N mu E plus this term plus this term. So both term had been included here, that is for the holes this term has been included here, and for the electrons this term has been included here. So this is the expression of the total current density in a semiconductor because of the drift current and diffusion current. And if both the currents we want to find out in terms of the whole current, then the expression will be JH will be this one, and we want to find out both the current in terms of the electrons, then this we can write it J equals to this much. So these are the expression which we have to derive to find out the total current density across a semiconductor material in terms of the drift current and diffusion current. This was the overall lecture for this class.